Hello everyone, am I audible? Can anybody just confirm? Hello?
Yes, you are audible.
Okay, thanks. Uh, we'll wait for a couple of minutes and then we'll get started. So, yeah, just hang on for some time. Hmm. इसमें वो इरेजर का ऑप्शन कहाँ गया? Hmm. So yeah, I think enough people are there, and we are already at 6:10, so we can start. Uh, yeah, actually, before that, let me just one thing I have to check. How many are there? First of all, am I audible? I think somebody has confirmed that. And is my uh, it's not a slide actually, it's my notes. So is it visible? Can anybody confirm?
Yes, sir.
Okay, yeah, thank you. Uh, so actually, people are still coming slowly. So I think I'll just wait for a minute or two because see, again somebody joined. Anyway, so we cannot wait forever. So first of all, my name is Akshay. I am a PhD student in Mechanical Engineering Department of IISc Bangalore, and as you know, for the uh, for this course of one second, yeah, for the fluid mechanics course on NPTEL, I am one of the TAs. I think the first session took place yesterday, and uh, so anybody uh, having doubt from that session also can ask today, or maybe we'll discuss it in some another, maybe not a conventional fashion. It is more like a discussion, not a class. So I expect some participation from your side. And yeah, so I think okay, one more person is there. Uh, so yeah, uh, before starting, hmm, just give me a minute. I have to just see one setting. I'll wait if somebody joins. Otherwise, we'll start in a couple of minutes. Hmm. So yeah, I think it's 6:15 now. So let me just see if anybody's in the lobby. Yeah, I think uh, no more. Uh, Nobody's waiting in the lobby anymore. So anyway, we can start now. Since this is the first week discussion, uh, uh, there are different things that we can discuss, uh, and I mean, uh, as there will be like total 12 such sessions from my side. So as we proceed in the course, we will be having very specific discussions. For example, next week we'll be discussing fluid statics. So uh, one second, Christy, Matthew, can you just mute yourself? Some background noise is coming. Okay, yeah. So where was I? Yeah. So basically, today we will be having a general discussion as to get ourselves familiar with uh, you know what this subject is all about, because if you had gone through the course list of courses offered on NPTEL this semester, there will be multiple courses on fluid mechanics. So there is this course fluid mechanics, then there will be some advanced fluid mechanics. There will be something called as computational fluid dynamics. There will be something called as fluid mechanics and its applications. So it's a very how should I say? It's a very diversified field of science. But here we will constrain our or keep our focus on the uh, introductory or basic concepts, at least for this class, and going forward when the discussions become more specific, like fluid statics, fluid kinematics, boundary layer theory. So there we will be particularly talking about those topics. But for as far as today's uh, discussion is concerned, it's a, how should I put it? I mean, it's a this thing. It's not a very gen like it's a general discussion, and I hope this will help you in clarifying some of the basic concepts in fluid mechanics. Uh, so we'll start about it, but before going into any, so see, as far as my class is concerned, I'm supposed to take numericals and solve them, and uh, the numericals will be more or less relevant to your assignments. So that is what is the scope of my class as defined by the uh, management people. But I don't like to teach that way, because that becomes very monotonic. Because if you just want to solve some problem, you can just Google, or nowadays you can ask ChatGPT. So then what is my contribution to it, right? So anyway, so therefore, what I do typically, I've been taking these classes since last, I think, 2 semesters. This is my third semester for NPTEL TAship, and what I observed is students don't respond, uh, actively to such sessions where you just discuss problems and solutions. But if you like mix it up, and if you just give some additional insights, which after studying more number of years in this field that you get with students, that is more appreciated, and I like to follow that only. So uh, so we'll start the main discussion now. This was all just a preface or introduction. So yeah, first question is, one second. I hope my handwriting is understandable to all of you. If not, let me know. I'll try to write it in a bigger font or maybe slowly, something like that. But I think this is fine. So the question is, since we are here to study or discuss fluid mechanics, first of all, can somebody just quickly tell me what is fluid as per your definition or as per your understanding? You can raise your hand or you can type it out if you are in a noisy place. That is also fine. Okay, so uh, yeah, uh, Taushif Taushif has raised his hand. And sorry if I
Yes,
did
sir.
not. Yeah, yeah. Is it Taushif? Please excuse me if
Yes,
it
sir,
is.
Tausif.
Okay, Taushif.
Sir, anything which can flow is called fluid.
Uh, okay, that is one aspect of it. Uh, but mm, there is something more to it. Can you just maybe think about it? It's okay if you don't know, but if that is the case, then water in a tank should not be a fluid, right? Because it cannot flow; it can just stay there. So anything else that is missing here? Pradeep Naik is saying any liquid or gas is a fluid. Uh, See, this is basically this answer is like chicken and egg story. So when I ask what is fluid, you will say any liquid or gas, and when I say what is liquid or gas, you'll say it's a fluid. So that is classification of fluids. Fluids are classified as liquids and gases. Typically, there is something called as I think plasma is also there, but that is out of our course scope. So okay, so I'll come back to the question: what is fluid? Uh, Toshif answered it, but it's I would say it's a 50% answer. There is something more to it. So, and at least I mean this is a technical or maybe undergrad level discussion. So more is expected. So anybody who knows the missing piece of the puzzle can just let me know or type it out. Okay, so 1 second. Yeah, so when I say fluid, first of all, uh, it is a matter or a type of a matter uh, which 1 second. Mm, okay, I'll just write it out. Type of a matter that deforms continuously under the action of shear force. So this is like the technical definition of it. So there are multiple things to be noticed here. So since it's a matter, it will have some volume and some mass. So that is there. I think that is understood by everybody. And key word is it deforms continuously. It's not like uh, okay. Toshif is asking, should I note it down? No, no. I'll share these notes with the NPTEL team, and they will make it available for you. So no need to write it down or something like that. This recording will be uploaded on YouTube also. So if anybody missed something in between or joined late or had to leave early, uh, they can see it later on the YouTube channel. That is also shared with the PMRF, sorry, NPTEL team. So don't worry about it. Just focus on what's being said here. And these notes are, or when I type it out, it actually helps people understand it better. Because if I just speak for 2 hours, most of you will be zoned out because nowadays our attention span is quite short because of the social media and all. So anyway, so that is the reason why I type it out. I could have just said it also, but once again. So yeah, it needs to deform, and it needs to deform continuously and under the action of shear force. So if anybody asks you in future what is fluid, just make sure that you mention these two things in your answer, that it deforms continuously and it is under the action of shear force. 1 second. So why do I say continuously? Because see, if you consider a solid, and if you apply any type of force, let's say shear force or normal force, solid also deforms. But let's say within a elastic limit, when we apply a force to a solid, it deforms, and when you start applying the force, it will come back to its original shape, right? And if it's beyond the elastic limit, it will deform for a certain period of time till certain length, and then it will break down. So there is no continuous deformation in case of solids, but in case of fluids, uh, fluid will keep on deforming as long as you apply shear force to it. So that is second keyword, shear force. So there are two types of forces. You must have, or you might have heard about them. One is shear force and one is normal force. So shear force is a force that is applied tangential to the surface of the object where the force is applied, and normal force is along the normal perpendicular to that area. So these two things are important when somebody asks you what is fluid. And next question is, what is fluid mechanics? So now we know what is fluid. Now this second word which is in the name of the course, what is fluid mechanics? Can anybody just tell me what do you mean, or what do you uh, understand when I say mechanics or fluid mechanics? Anybody?
Sir, it can actually deform in normal force also, is it not? The fluid.
Not really. For deformation it should have shear force. Normal force will uh, compress it if it's compressible, but I mean, it won't deform continuously. It may deform. This is something called as volumetric strain. There is something called as volumetric strain, but it is not continuous. So it needs to deform continuously under the action of shear force. And if any matter satisfies this definition, that is the fluid. And yeah, as somebody earlier had said, that fluids are typically classified as liquids and gases. We can go into deep here as well, what is liquids and what is gases. But typically speaking, liquids are fluids that have higher densities, gases have lower densities. But there is another property which is used to define fluids, which is called as viscosity. So liquids are more viscous, gases are less viscous. That is not true for all cases. Okay, it's general observation. You can always find some outliers, but these are general things that you should be aware of. Yeah, and coming back to the question, fluid mechanics. Somebody said, Disha Mishra said, to study rate and motion. Okay, so I mean, you can go and look for the textbook definition of mechanics. It will be there. But what I understand from this fluid mechanics course is, here we are interested in uh, how the fluid deforms under the action of external force, and what is the resultant effect of it in terms of, let's say, force or pressure. So that depends on your application, what you have in mind. But when I say fluid mechanics, it is basically a study of branch of a science which studies deformation of fluids under the action of external forces and the consequences of it. So that is the brief introduction of fluid mechanics that I have understood over the number of years. And yeah, so basic is like fluid and fluid mechanics is out of the way. So
can you write down the definitions a little bit? Sorry for this.
yeah, it's written here, right? Type of a matter that deforms continuously.
All
Oh,
right.
fluid mechanics. Mechanics,
Yes,
you are saying.
yes, yeah.
Okay, I can write it down, but it's not a textbook definition. So
Yeah, it's okay. Not a big deal.
what is fluid mechanics? So, but branch of science that deals primarily with deformation of fluids under the action of external forces and their consequences. So this is like a, a condensed version of it, but yeah, this like captures the essence of this course. So now this is out of the way. So now the next question should be, what are we discussing today apart from this basic things? So let me just take a moment and see what type of questions were asked in your assignments so that I can gauge, uh, you know, what else should we discuss. So this first, like week 0 prerequisite assignment, it was, I think it is basic introduction of concepts such as pressure, Reynolds number, mass flow rate, uh, you know, something like that. And then there was introduction to, I think, yeah. So basically, what I'll do, I'll not go into details today because we have a dedicated lectures for each topic. But one second. Yeah. So there is one more concept which is this thing. So basically, you can apply this like. So basically, fluid mechanics, as I said earlier, there are different approaches to study fluid mechanics. So one approach that we are going to study is called as a classical approach, and it's not a question actually; it's a classification. So I can write, let's say, fluid mechanics. If you want to study it, what approaches can you have? Basically, that is the classification based on one type of classification. So one is called as classical. Let's say I will use FM as a short form for fluid mechanics. One is called as classical fluid mechanics, and then there is another branch of fluid mechanics which is called as statistical fluid mechanics. So, as the name suggests, statistical fluid mechanics is nothing but the uh, approach where you study at a very microscopic level or even atomic or molecular scale, length scale. So basically, you study motion of fluid molecule or fluid atom. I think it's molecule mostly. Fluid molecules at very small scales, length scales. So that is, and based on such study of such small molecules and you take a large number of those molecules and studies them, and you get some statistics out of it, and that is called as statistical fluid mechanics. So maybe if I have to summarize it in a one word, it's not molecular. I should write microscopic. So it's a study of fluid particles at very small scales, but that is not our approach here. What we study, or what we are going to study in this course, is classical fluid mechanics, which is macroscopic. So macroscopic in a sense, we don't go at the individual molecule level and see what is happening there, or very small number of fluid molecules. No, we don't do that way. What we do is what we study is classical fluid mechanics, which is macroscopic length scale. So basically, we consider fluid as a bulk and study the bulk properties. So when I say water has density of 1000 kg per meter cube at normal temperatures and pressures, I mean not an individual particle of water that I'm watching. It is for a macroscopic amount of water, which is like a bulk amount of water. It can be in grams, milligrams, kgs, or even tons, but we don't go microns, pico, and that scales. So that is the classic fluid mechanics approach. And sometimes people define this as a continuum approach. Continuum approach. So basically, you assume that the matter or the fluid that you are discussing is continuous in nature. There are no discontinuities. So basically, when you study at a molecular level, what happens? You will have one molecule flowing from one place to another. Then there will be discrete gap in time and space where there will be no molecule, and then the next one will come. But in classical fluid mechanics, it doesn't happen that way. We assume that the fluid particles are present at all points of our domain, and then we study them. So that is, which is classical fluid mechanics approach. And yeah, so that is one thing. And then there is yeah, so as I said here, fluid deforms continuously under the action of shear force. So that is typically written in this fashion. 1 second. So I'm assuming you might have seen this pictorial representation of this law of viscosity. So basically, fluid is flowing in this direction, and this is our y direction. So and as it is a shear force, it will be applied on the surface or the interface that will deform the fluid, and so this this angle essentially is this rate of deformation of fluid, and then there is a constant of proportionality, which is nothing but the viscosity. And this is true for, like, there are some fluids which obey these laws or this law, and there are some fluids which don't obey this law. So the fluids that obey this law are called as Newtonian fluids. So fluids that obey this relationship are called as Newtonian fluids. Okay, so then as the name suggests, if some fluids are Newtonian fluids, then there will be some fluids which
So you are not audible. You are not audible, sir.
am I audible now?
Yes, sir.
Oh, I don't know what happened. I was audible, I think, initially. Anyway, so yeah, then there is something called as ideal fluid, which does not exist in reality, but it is a idealization of a fluid in some hypothetical context. You should only remember two things about ideal fluid. It has zero viscosity, and I think that is the most important thing of it. And I think it is incompressible. It is considered incompressible as well. But this is not a real fluid. So as long as you just remember the concept that there is something called as ideal fluid and which has zero viscosity, uh, it's fine. Uh, I think that is okay. And then there is another type of one second. Sorry.
But sir, we learned any fluid has viscosity. We learned that somebody told us. Any
Yeah,
fluid has viscosity.
any real fluid has viscosity, however low it can be. But this ideal fluid, it does not exist in practice, in reality. So it is just I mean, I am telling you because you might see this as an option in some of your questions or in some competitive exams. So, ideal gas, typically we discuss that in thermodynamics. So, in reality, mm, nothing is ideal. So, in context of fluid mechanics, you can define ideal fluid which will have zero viscosity and it will be compressible. And I think there are some additional properties to it, but it does not exist in real life, and therefore we don't study it in this course also, but it is there. This, I am just introducing the terminology. It's not a real thing, so don't get carried away too much on this. In real fluids there will be some viscosity and there will be some additional behavior, change in behavior also, that we'll discuss now. So which is, I will just say, classification of fluids. And there is very one famous diagram. Uh, one second, I'll just pull it up. Mm, in which yeah, so I'll just so on y-axis you have shear stress, and on x-axis you have this velocity gradient or rate of deformation of the fluid. And Newtonian fluid is typically a fluid which shows okay, one second. So this is origin. Okay, so this is Newtonian fluid. And because here your tau is directly proportional to the gradient, so therefore you have a straight line. It will have some slope, which will be your this thing, what you call viscosity. And then there are some fluids which what you call them, they don't show this type of behavior. They show slightly different variation, which is like this. You will not get a linear relation out of them, but you will get something like this. And in this second line that I just draw, the curved line, there your shear stress is increasing with respect to the du by d velocity gradient, but it's not a linear relationship. And initially the deformation is more like you apply a small load and then it deforms, but after a certain time, if you want to deform it, you need to apply more load. So basically uh, that is the relationship between tau and du by dy. So these type of fluids are called as dilatant. And then there are some fluids which exhibit this type of behavior. So in this case, initially you need to apply more force, shear force or shear stress on that area, and then uh, after certain threshold value or gradually the velocity gradient increases, and then you need not to apply more shear force. So these type of fluids are called as uh, pseudo plastics. And one second. Then there are another type of fluids which are called as like plastics. So basically, as soon as you apply the force, they won't deform. For some time, they will behave like a solid, and there won't be deformation under shear stress. But what happens after a certain time, they start deforming, and that is how you get the deformation or rate of deformation. So they will typically look like this. So there is some initial tau 0 that you need to apply, and after that only you will see some deformation that will be visible to you. So when they show this linear this thing, what you call linear variation after that initial tau 0, they are called as Bingham plastic. I will write it here. And then there are also some fluids which after initial application of tau 0, when they start to deform, they don't deform linearly. They deform something like this as well as something like this. So as in the case of this Newtonian pseudo-plastic dilatant, there are 3 types also with Bingham plastic, and this thing. Other 2 types are called as, this is thixoplastic, and I think this is a rheopectic or rheoplastic, something like that. Rheopectic maybe. You can cross reference the names that I'm putting here, but you get the idea, right? Uh, it's not like one second. It's not like every fluid, as soon as you apply the shear force, that will start deforming. It doesn't work that way. And you know this sometimes this velocity gradient, it is called as strain rate also. Okay, so keep in mind this velocity gradient, or oh, this is not 1 second, sorry. Yeah, this is thixotropic, and this rheopectic is okay. Yeah, so just to be sure, I'll just clarify this, that sometimes on the x-axis, instead of du by dy, you may get strain rate. In some books, you may see this. So basically, strain rate is this deformation with respect to time. So if you just do some geometrical manipulation in this figure that I shown here, then you get that the velocity, rate of change of velocity is equal to the strain rate. So that is there. And yeah, coming back to this diagram, I have one question. Okay, and this is called as this y0. Sorry, tau 0 is called as yield shear stress. You may not need to remember this or mug up these things, but you should at least have some feeling as to what we are talking about. So my question to you is, as I said, there is something called as some hypothetical fluid which is called as ideal fluid, and then there are some solids. So if on this figure where we have tau on y-axis and velocity gradient on x-axis or strain rate, where will the ideal fluid lie? Or if I want to show the ideal fluid line, where will it be? Can anybody answer this question? First of all, did you understand the question?
So it does not lie anywhere.
Okay, so somebody said it does not. Pradeep, I think. Yeah, Pradeep said does not lie anywhere. Anybody else?
Can you repeat the question?
Okay, so here you see 6 types of fluids, right? Newtonian, dilatant, Bingham, plastic, etc. My question to you is, if I want to show ideal fluid on this plot, what will be the relationship between tau versus du by dy for an ideal fluid? Keep in mind, ideal fluid does not have any viscosity. It is a hypothetical fluid with zero viscosity. So,
So it will be a straight line at the 0 of y.
okay, there can be
Maybe.
but that does not narrow it down, right? Because this Newtonian fluid line is also a straight line starting at the origin, right?
Yeah.
So you are going in the right direction, but see, if any fluid does not have any viscosity, even if I apply very small shear stress, it will keep on deforming, right? Because there is literally no viscosity. So therefore, it will have, like, in a limiting sense, it will have infinite strain rate or velocity gradient with very small tau. So therefore, that line should be something like horizontal line, and
Yeah.
it will be like close to origin, but there should be some non-zero tau, right? So
Okay.
like that. I mean, you can apply any tau to the ideal fluid, it will keep on deforming because it does not have viscosity. So the deformation, it's literally independent of whatever tau you apply, but typically for very small tau, it will start deforming very high. So that is ideal fluid.
Okay.
These type of MCQs are generally asked in some competitive exams, maybe in GATE exams or something like that. But yeah, so the next important part of this discussion is examples of these type of fluids, because in this
Sir,
course,
one question. When
yeah,
you say ideal fluid incompressible, means it cannot be compressed, means it
yeah,
cannot be deformed, means it cannot be deformed.
no, compressible incompressibility comes in the context of normal force. In the case of shear force, it doesn't matter whether it's compressible or not. It will deform. When you say it is incompressible, that means like when you apply normal force to it, it won't budge. 1 second, something is in the lobby. Okay. So now going ahead. So basically, the next important thing is why do we like in this course? What we are going to study? Like there are like so many types of these things, right? So many types of fluids. So to narrow it down, I will try to discuss examples. First is Newtonian fluids. 1 second, just give me 1 second. So basically what happens is in like the most abundant fluid that is available uh, on the earth is water, right? And this water is a Newtonian fluid. So basically you will observe linear relationship between tau and velocity gradient or strain rate. So therefore the most important fluid is water, that is Newtonian fluid. And after water, there is the most important fluid, which is air, that is also Newtonian fluid. So, and some alcohols. So, alcohol is not that important, but water and air are basically Newtonian fluids. You will observe linear relationship between them, and therefore, in this context, for this course, our discussion is primarily focused on Newtonian fluids. So, because majority of practical fluids that we are going to encounter in practice are this thing, Newtonian fluids. Then there is 1 second, dilatant fluids. I had this diagram, but it's something there. Yeah, so dilatant fluids are, so see, basically now the other categories of fluids, there will be some examples for that, but you know, these are not like abundant fluids, and therefore we don't encounter them in much in practice, but they are there. So basically corn plus starch mixture and sugar syrups. So something like this, and this then there is next thing is so now Newtonian dilatant, then there is pseudoplastic. These dilatants are also called as shear thickening. This is just a term that you should be aware of. So what happens, like shear thickening, as the diagram suggests, what happens when you apply more and more shear force, it becomes the velocity gradient or the strain rate becomes less and less. Like no, the rate of it is like that. No, so basically, therefore, it is said that it thickens with application of more stress. So therefore, they are called as shear thickening fluids, and the pseudoplastics, they are called as shear thinning. So basically with the application of more and more shear force, they keep on becoming like easy to flow, like their resistance to flow, which is viscosity or the velocity gradient, it decreases. So like that. These I'm say, don't get confused, or maybe if you are not interested, don't pay too much attention to this topic also. But my point is, these terms you should be at least, if when you are going and say I study fluid mechanics, these things at least you should be aware of. So in this case, the most important example is blood. So you might have heard that when you do blood test or something, they use this thing, but not in directly. So they anyway. So leave it at that. So blood is there, and I think paint also comes in this, nail polish paint. So like that. So Bingham plastic, etc. I mean, we can discuss. I think Bingham plastic is toothpaste. One second. As far as I remember, most important Bingham plastic is toothpaste, and I think it was asked in GATE exam also. Yeah, toothpaste and mayo. That mayo sauce that we eat. And what else is remaining? Rheopectic. So these are like very, special type of fluids, not easily absorbed. So I'm just giving you some examples, but they are not that important, I think. I mean, not important. See, this rheopectic, I'm not finding example also. Yeah, so there is one example for rheopectic, which is I think gypsum suspension in water, something like that. So initially it won't budge, but after a point it will start deforming, and then it will become hard and hard with the application of more shear stress. And for thixoplastic, I think the important one is lipstick, I think. Yeah, something like that is important for it, because see, these type of very small questions, they will be asked in your competitive exams. In this course, maybe not much, but you should at least know what is what. So thixoplastic, see, I am not even finding good examples for it. Anyway,
Rubber, sir, rubber.
Rubber, huh? Are you sure?
Yeah, rubber.
Okay,
Yeah.
we'll put it. So it is my sincere request to all of you who are attending this lecture. I have given these examples, and there will be some more examples. So if you are interested, please cross check this. And the key takeaway point from all this discussion is this one. So the most important fluids that we are going to study are water and air, and they are Newtonian fluids. And therefore, for Newtonian fluids, we typically use this relation to solve the problems later on. So this is the whole conclusion. We have spent some 5-10 minutes on it, but it is good that you should know other things also. So that is there. Let me check if this is. So I think in your assignment, yeah, there are some questions on this topic. I think you can answer this. Yeah, okay. This ideal fluid is in your assignment question. So yeah, maybe you can. I think I have given you the answer directly. But anyway, 1 second. Now next, what should we discuss? See, this is actually introductory class, right? So I think this surface tension, capillary, what else is there? I think those are also should be covered in this one. Let me just confirm this. Can anybody just tell me that what all concepts were covered in the first week lectures? This is just a test for you that have you seen the lectures or not? Anybody?
Hello, sir.
Yeah, tell me.
There is a concept about a capillary tube that was taught,
Mhm.
and there is also, wait, I'm forgetting again. Yes, capillary tube was a difficult concept for me, so I remember that concept. It was taught in the lecture.
Okay.
That's all for.
Yeah, I was also thinking that only because when you discuss basic properties of fluids, those are typical things that you discuss. So basically, when let's say my question is, why do we study capillary, etc., capillary rise or fall, whatever it is? Can you give me one very important example in real life where this capillary action is very important? Anybody? It's very common or very, very important.
In the case of plant, when plant sucks out water from the ground, I think there is a capillary concept there.
Yeah, that is correct. Because in plants there is no artificial pump or something like that. They have to suck the water, and there are some very tall plants also, right? So based on this capillary action, the water is sucked from the ground and it reaches till the top of the tree. So that is we don't appreciate the fluid mechanics there, but it's quite uh, astonishing. So anyway, so this I think all of these are covered in the class. Maybe we can take some problems, but yeah. So before going to the capillary discussion, can anybody tell me, have you heard about this thing which is called as, 1 second, no slip condition?
Yes, sir.
Anybody? Yeah.
Zero
tell me.
velocity. Zero velocity.
Where?
Sir, just at the like pipe, like just at the pipe, at surface of the pipe.
Okay. So let's say this is the interface. Let's say I'll just highlight it like this. This is the solid, and let's say some fluid is flowing on the top. It may be liquid or whatever it is. So in this case, what happens? The first layer, that, like, if you just zoom in and see what happens, the first layer of fluid molecules that come in the contact with the solid surface, they kind of stick to it, and there is no relative motion between the first layer of fluid molecules and the top layer of the solid surface. And what happens? The next fluid molecules that come on after the first layer, like this, there will be some motion because intermolecular forces of attraction in the liquids, they are not that strong like solids. So there will be some relative motion, and extent of that relative motion is defined by the viscosity of that particular fluid. So therefore, uh, uh, like this no slip boundary condition is very important in the context of fluid and solid surfaces. So now that most of you know, my next question is, can you tell me some example where this no slip boundary condition is not applicable? Anybody?
Space.
In space, there is no fluid, right? So there is no.
Yeah, like I just imagine the fluid being floated around. So
No. In vacuum, there is
kind of.
no fluid. So that is not classical fluid mechanics. That comes in the statistical fluid mechanics. If at all there are some fluid molecules present in the vacuum, but let's not go there. There is a very common
Okay.
example
Yeah.
that is observed in real life. Very common. It is typically not, studied. Therefore, this is like the trick question.
Yeah.
So just think
Okay.
about it.
What if
Yeah, tell me.
it may be a phase between fluid and gas?
Yeah.
How it works?
Yeah, basically, instead of solid, if you replace, let's say there is another interface and you have fluid 1 at the top, let's say air, and fluid 2 at the other side of the interface, let's say it is water. So in this case, since there are like this is I mean, instead of talking hypothetically, I will give you an example. Let's say soap bubble. So if you have a soap bubble, right? So if you just zoom in, oh my god, my circle is very bad. Okay, so there will be air outside, there will be air at higher pressure inside, and there will be liquid film, right?
Yeah.
So here what happens? There is no there is see in solids, what happens? Solids are having stronger intermolecular attraction forces, therefore they don't deform easily when you flow the fluid on top of it, and therefore
Yeah.
the first layer of fluid sticks to it. But in case where there are both sides there are fluids, what happens? Both fluids will deform, right? So
Yeah.
on this outer interface as well as on this inner interface, you cannot apply slip boundary condition. No slip boundary condition is not applicable here. And then there is something called as slip boundary condition.
Okay.
So there, basically, you don't take velocity as zero at that surface at
Okay.
interface. And one more example is there where no slip boundary condition doesn't apply. It is in the as I said earlier, some microfluidics, channels are there. They fall under the continuum or the classical fluid mechanics domain only, but they are very, like, let's say if we see a pipe, normal pipe is of the order of centimeters, millimeters, right? But let's say if I construct some artery wall for human heart, uh, it will be of the order of some few hundred microns or something like that. So that still falls under the category of con- classical fluid mechanics, but length scales are very small. So there sometimes no slip boundary condition does not apply because there are some other forces at that small, at very small diameter or length scale that become dominant over the intermolecular forces. So there, also boundary condition or no slip boundary condition is not strictly followed. So there can maybe if some of you are interested in higher studies or something like that, maybe just keep in mind that this also happens. Then yeah, what else is
So
there?
in case of turbulent flow, also no slip boundary occurs. Turbulent flow.
Yeah, very good question. So if you see turbulent flow, maybe I'll draw it here only. So this was the first case, this was the second case. Let's say the turbulent flow third case, if you take, we'll consider turbulent flow over a flat surface, let's say, just for our understanding. So what happens if you zoom in, let's say this is that surface, solid surface at the bottom. Then if you just observe it, it may look like, you know, in turbulent in turbulent, the velocity vectors of fluid particles, they keep changing as per their location as well as their time. So therefore, and there will be some eddy or vortices also. So turbulent flow is a very difficult, fluid phenomena to study analytically using some equations and all. It's very difficult. So, but if you zoom in on this interface, what is observed is, I'll use some different color, very close to the surface, there is a very small layer which is called as viscous sublayer. If you zoom in, then what you will observe is this is again the interface, solid interface. But here in this region, there is similar behavior as the laminar flow. So there will be orderly motion between the fluid particles, and the first layer of fluid particles will stick to the surface, and then typically what is the laminar flow, which is, orderly fashion flow that will take place. So even in case of turbulent flow, no slip boundary condition is applicable. The difference between the laminar flow and turbulent flow comes after this viscous sublayer. So basically, very close to the surface, there will be viscous sublayer. Then there will be something called as this layer will be there. That is called as buffer layer. And then there will be your turbulent flow. So there is a dedicated field of fluid mechanics which deals with turbulent flow and how they develop. And but as you asked, and that is very good question. In case of turbulent flows also, this is valid. This no slip boundary condition is valid. Okay.
Sure, thank you. So the buffer layer thickness will be varying from place to place.
Yeah, actually, in case of turbulent flow, this surface characteristics are also important. See, in laminar flow, if you have a very smooth surface or slightly rough surface, as long as it doesn't disturb the bulk of the fluid motion, there won't be any significant consequence. But in case of turbulent flow, the surface roughness is very important. And as you said, this velocity and other things, density, etc. are there. But one additional factor that comes into picture in turbulent flow is the surface roughness. So if you go and see any standard book on turbulent flows, there they define everything based on the wall distance. So basically what they do, they start from here. Okay, 1 second. So this is your interface, right? So they take it as y equal to 0, and they define something called as wall units. So, normally we have Reynolds number which separates laminar flow and turbulent flow. And in case of turbulent flow, there is something called as wall units, which is used to separate between the thickness of viscous sublayer, then the thickness of buffer layer, and then there is the thickness of turbulent flow. I have studied this a long time back. So till 5 wall units, I think it is viscous sublayer, and from 5 to 30, it is buffer layer, and then from 30 onwards, it's a pure, turbulent flow. So like that they define there.
30
Okay.
centimeter. 30 centimeter. You tell.
No. That is what this wall units is a different number. At this point, we are not in a position to discuss that because I had not studied it for it. But this wall unit is not in meters. Okay, it is a dimensionless number. It is a scaled number. So
Oh yes, yes.
yeah, so like that. Okay, so since we are discussing that, maybe it is relevant for our discussion in future. There are some important numbers that we need to understand. First is called as famous Rayleigh number. So, can anybody tell me the formula for Rayleigh number? Anyone? First of all, have you heard this Rayleigh number and something like that exists?
Yes, I did. Really.
Okay, good. Then, can anybody tell me how do you define Rayleigh? Or is it not covered yet? I think maybe it's not covered yet, but just let me check the notes if it is there or not. If not, I'll just leave this topic to discuss in the future. Okay, I think it is not discussed, so let's skip it for now. Maybe next time we'll
No,
come back to.
you can just tell us three, just 1 or 2 sentences.
Pardon?
You can just tell something. Since you mentioned this, kindly 1 or 2 sentences. You can just mention what is this actually.
Okay. Yeah, I'll let you know. See, what happens? How should I say? This thing. Let's say. So there is a laminar flow in which your fluid flows in orderly fashion. So like this, you can define it like this. And in case of let's say you were to get the laminar flow, you were having some mass flow rate of the fluid, and then you increase it. You keep on increasing it. So what happens after certain mass flow rate or certain velocity of the flow, it becomes turbulent. So the turbulent flow is nothing but disorderly motion of the fluid particles. So you will not observe like linear or smooth motion. There will be something like abrupt motion. They will have different sizes, etc. So there is a transition point for, let's say, if you are considering a flat surface. So if your Reynolds number is less than 1 lakh, it is considered as laminar, and if it is greater than 1 lakh, or maybe I think 5 lakhs, it is I think it's 5 lakhs or something. Let me just once confirm. I think it is 5 lakhs. Flat plate. But see, this number doesn't matter per se, but yeah, it is actually varying. So it is between let's say some of the order of 1 lakh. And then it becomes turbulent. And for pipe flow, it is different. But my point is, this is not the significance of Reynolds number. See, Reynolds number is typically, if you see for this example, it will be defined as rho v L by mu. So rho is the density, v is the average flow velocity, L is the length of the flat plate, and mu is the viscosity of the fluid. But this is like the formula for it. It is available everywhere. But my point is, my question was not that. My question was, what is the significance of Reynolds number? So if you can see in the numerator, you see here density, right? And
Yes.
density is measure of inertia of fluid. So so if the density is more, for example, water has like 1,000 times more density than air at normal temperatures and pressures. So if I want to make air flow versus if I want to make water flow, since water is denser, I need to apply more shear force to it, right? Otherwise, it won't flow that easily as compared to air. So this density is basically a measure of inertia forces, and at the denominator you have viscosity. So viscosity signifies, the resistance to the flow. If any fluid is highly viscous, then you will need to apply more force for it to flow, right? For example, if you consider again air versus, let's say, engine oil or something like that. So in that case, the denominator represents viscous forces. So Reynolds number is nothing but a criteria which tells you there are two important phenomena or forces that are, uh, you know, that are governing the fluid flow. And let's say when Reynolds number is very small, so in that case, what it means is inertia forces are negligible as compared to viscous forces. So basically, that means the whole fluid flow is dominated by viscous forces. And I think this happens in plug flows. There are different types of flow regimes. Maybe that is not in the course purview of this course, but based on this this classification, you get different type of flow regimes. So there is something called as plug flow, which comes under this case. And on the other hand, when Reynolds number is very high, your inertia forces are dominant. They will govern the viscous. Sorry. So what I mean to say is, what is the conclusion of this discussion is, when your Reynolds number is very small, that means your inertia is negligible as compared to viscous forces. So in that case, you need to give more importance to the viscous forces that are governing the fluid flow. But in case of the other case, where Reynolds number is very high, which is turbulent flow regime, there you need to focus more on these inertia forces. And the same is observed here, right? See, I draw here one small layer. So in that small viscous sublayer, only the viscous forces are dominant. But if you go outside in buffer layer or turbulent layer, there inertia forces are dominant. So like that. So Reynolds number is, if anybody asks you in any technical interview. And this is actually very typical question that is asked. So just don't say that it is rho v d by mu or rho v L by mu. You can just give a some technical answer like Reynolds number is the dimensionless number which determines whether inertia forces are dominant or the viscous forces are in the dominant for fluid flow, like that. So there are different numbers. We will discuss them later. I think I think in boundary layer it is there. So we'll discuss more there, but this is the main crux of that. So yeah, I'm just seeing what all other things are there. Okay. I'm just going through the first assignment and then seeing that we are covering most of it. Okay, so there is this discussion regarding the viscosity and its change with respect to the pressure. Okay. Okay, 1 second. Yeah, so that viscosity and all that you can see later, but we will just discuss briefly about the this thing, what you call surface tension. Can anybody tell me what is surface tension or why is it important? I think somebody's camera is okay. In chat, somebody was asking how lipstick and rubber is fluid. Oh, see, lipstick. If you see, it's not a fluid. It doesn't look like liquid or air or gas. But when you rub the lipstick on some surface and you keep on rubbing it in a straight line, what happens? It will start, like that. It's not an exact fluid motion, but it will mimic it in that way. So you have to imagine that way. And yeah, it is a recorded session. It will be on YouTube, I think, after some time. Okay, so coming back to the surface tension. First of all, anything that comes to your mind when I say surface tension? Anybody?
So tension on the surface. Tension on the surface.
Okay. Yeah. So, okay. Can you fluid exerts a force on the surface? Okay. Okay. So yeah, basically, if I remove the surface part and if I just ask what is tension in a string or something like that, it is like when you apply force on its end, and the force should be in a outward direction. Like for example, this is the typical example that we study in our 11th, 12th, right? So there will be some mass. There will be some massless string attached to a pulley, and there will be some another mass. Okay. And there will be some another mass. So it's a very common problem in JEE and all. So here, when you draw the free body diagram of this string, what you say that there is a tension between this. So you take, let's say if I draw the free body diagram of this mass, it will look something like there will be tension and its own weight will be balancing the tension in the string, right? So the point that I'm trying to make is, and here for this mass, it will be mu into its normal reaction, and that will be balancing the tension in the string. So tension, tension is always, acting outwards. So let's say if you have a, you have, let's say you have a fluid surface, and when you apply a tangential force to it, for example, this is the fluid surface, okay, and you are seeing it from the top view, like that. And if I apply some tension force, like if I am stretching it, so then it will, after some time, it will deform. Let's say it deforms in one direction and it becomes like this, okay. So if its length is increasing, its width will decrease, right? So the amount of energy that I put to stretch this fluid surface or film, divided by the area of the film, is called as the surface tension. So basically, it is energy spent in stretching the liquid, not liquid, I should say. It should be fluid film per unit area. So typically when people ask surface tension, or maybe if somebody asks you what is surface tension, you should explain it this way, that it is the form of, or it is the surface tension is the quantity that defines how much energy needs to be spent in stretching that fluid film per unit area. So that's why if you see, units of surface tension are, can anybody tell me what is the unit of surface tension in, let's say, standard units? It is typically Newton per meter. So what we think is, it is basically force per unit length, and many people define it that way, that when you apply a force on a surface and it stretches by, let's say, some length, then the force applied per unit length is called a surface tension. But that is not the correct way. It is actually like this. It is the energy which is in joules per area of that film which is your stretching. So eventually this joule is defined as Newton meter, right? Which is, and therefore it becomes Newton meter. So, but it is better to define it in the form of surface energy, is the thing. Okay, so that is there. And apart from that, yeah, so so now there is this derivation of it. So let's say we take a, it should be circular, sorry. Yeah, so let's say it's a liquid drop, and now again the question is, you need to find how much energy was utilized, to form this drop, and surface tension is basically the resultant of that energy per unit, whatever area it covered. So here, generally, what they do is they take a cross section area like that, and you will see something like this diagram, which is like semicircle of it, and they draw it this way, and they will show on circumference the surface tension forces, and at the center there will be pressure forces, pressure into, or let's say pressure force, and on the surface you have surface tension force. So actually, when I first studied this, I did not understand it. Why did they divide the drop into half, and what did they do? So basically, it comes from here. So here also, what you did, you cut the string and you did the free body diagram, and then you realize that tension is equal to the mg, or in the horizontal case, tension is equal to mu n. So in the same case, what they do, they divide the liquid drop into two parts, and when they draw the free body diagram, what is observed is this inside the liquid drop, the pressure is higher, and that's why it tries to bulge that liquid. So therefore, these pressure forces are there, and surface tension forces keep that pressure forces in check, and so that the liquid interface is stable. If these two forces doesn't match, or they don't balance each other, then the drop will dissociate, or it will break down into a number of mole droplets, where the surface tension forces will be balanced by the pressure forces. So like that it goes. Sir, please can you share MI links? I don't know what is MI links. Anyway, so coming back to this, so now the derivation is straightforward. So for stable liquid air interface, the surface tension forces should balance pressure forces, right? So the surface tension on this area, but it is taken on the periphery, and the pressure forces are like delta P, which is pressure difference between atmosphere and inside the drop, into cross-sectional area, which is pi by 4 d square. D is the diameter of bubble, and surface tension is defined by this sigma typically, and it is on the circumference, because the film is on the circumference, and in this free body diagram, the circumferential perimeter is pi into d, 2 pi r or pi into d. So therefore, when you get the surface tension as this pi will cancel, and it will be delta T d by 4. Can anybody? Yeah, I think that is the formula. Just let me confirm once. Yeah, I think this is correct only. Yeah. So now the thing is, I have written it in a different way. Typically, at a given at a given temperature, the surface tension between any surface interface is typically fixed value. This sigma, which is, for example, if you take bubble or drop in air, so for water and air interface, this sigma value is defined. So typically we use this force balance to find the pressure inside the bubble, or this delta P is nothing but P, let's say liquid drop minus atmospheric pressure, that is delta P, and that becomes equal to 4 sigma by D. And if it is a liquid bubble, in bubble what happens, there are, instead of one outer surface, there are two surfaces. One is I think I have shown it here somewhere. Yeah, so one outer surface between air and the liquid film, and one surface between air and the liquid film from the inside. So this surface tension becomes twice, and therefore you have delta P becomes 2 into 4 sigma by D, which is 8 sigma by D. So like that. So if you understand this derivation, and I think more important than the derivation is the physical significance that you should take away from here. So that is there. What else is there? Capillary is remaining. Maybe we can discuss it, but capillary also more or less, you know. And one more thing is there. I think this question was asked to me also previously. What should I say? This, like, you can take it as a note that surface tension arises due to unbalanced cohesive and adhesive forces. So basically, cohesive means same molecules, and adhesive means different molecules. It is given in your notes also, but you know, it is this question is very important, and I think in many competitive exams it has been asked. So surface tension, why does it occur? It occurs because at the interface, you know, I should write at interface. At interface, what happens? There is a force imbalance between, let's say, if you consider a particle at the interface, and on top of it, let's say it's air, and at the bottom it is water. So on the surface, for a molecule on the surface, there is air on the top and liquid water on the bottom. So there is a difference between liquid and water and air interaction, and water interaction for that molecule, and because of this force imbalance, the whole surface tension is existing. So this is also a very important note. Please, you can remember this. And then there is capillary derivation is also there, but I think it is important. Like, you can get it anywhere. But one more concept I'll just briefly discuss, and we'll stop for today. It is called as angle of contact. So this also comes into the existence because of difference of surface tension between different type of surfaces. So there will be something like this. So this is a solid surface, this is, let's say, liquid, and this is air. So, or maybe not air, let's say any gas. So what happens if you consider this point? So here, if you consider outside, there is surface tension between solid and gas, and on this side there is surface tension between solid and liquid, and on tangent to the surface there is a surface tension between liquid and gas. Correct. So for different type of different type of solids, liquids, and gas, uh, this this will change. So for some liquids like water, etc., on any typical metal, this type of wetting will happen, or this type of drop will be formed. And here, angle of contact is defined as the angle between the surface and the tangent to the liquid gas interface and going through the liquid domain. So this is your angle of contact theta, and it is typically less than 90 degrees Celsius, 90 degrees, and maybe this is used in another field, but you should know that this is called as hydrophilic case, I think, and the other case is called as hydrophilic, in which you will have something like this. So here, what happens because of uh, interaction between solid, liquid, and gas, the droplet will not completely stick to the solid surface. It will like float on the top of it, and this is very interesting. We generally don't observe this in practice, but it happens, and that is also important. Here your theta is greater than 90 degree. So it is, I think, hydrophobic, they call them, these surfaces. So don't worry about hydrophilic, hydrophobic. That is not, I think, important right now. But there is this angle of contact, and one important question that is typically asked in the exams is definition of it. Because see, I can trick you like this, that I will say that draw any uh, liquid and solid interface and show me the surface tension direction and draw the angle of contact. So one thing that you should know is angle of contact is drawn in such a way that it will always pass through the liquid side, not the other side. So here in this figure, the angle of contact will always be like this, in this case of hydrophobic, not the other way around, not like this. So that is the wrong direction. So that is the only trick that can be asked in this. So like that. And then you can solve some numerical examples. I think one of them is in your assignment also. Okay, so that is regarding the capillary rise. I think we have 5 minutes. So capillary rise can also happen and capillary fall can also happen. So if you have a glass and if you put water in the beaker and put a capillary tube, it rises. But if you have mercury, it will dip. It will not come up. So like that, it will be there. So, one second. So in capillary rise, okay, it's actually got very quiet. Are you guys there or got bored and left? Okay.
No, sir, interesting.
Yes, sir.
interesting.
Yes, sir. We are there.
Okay.
Yeah,
So
hydrophobic, they are very interesting, sir.
yeah, so this is like the last part of the lecture. So just hang on for some time. And yeah, so capillary rise and capillary fall. The significance is already told by one of you. It is very important, and I told you, in some very small scale instruments like artery walls or something like that, where the length is very small, but it is still a continuum domain. There, capillary forces are like the predominant forces that are governing the fluid flow, and typically.
Capillary fall is something, sir, it is unique. Can you give some example?
Pardon?
Capillary fall, sir. Can you give some example? Give more examples. Capillary fall.
Yeah, one example is very famous. This in glass container, you take mercury and dip a small glass tube in the mercury. Then instead of coming up, the mercury goes down. That is capillary fall, and it is so whether the capillary rise will happen or capillary fall will happen, that depends on only this surface, this sigma between that solid liquid interface and this angle of contact. Let's say we call it as theta. So this theta between and theta. So, and also, I mean, if you see at the derivative and this diameter of capillary tube. So one second, I'll just do the derivation. You will realize what I mean. Just quickly do it because it's standard derivation. Oh, it doesn't do. I thought it will make it as a beaker. Anyway, so let's say this is your liquid surface, and we are taking, typically if you take water and glass as a material of the tube and water inside, it will show the behavior like this, and your water level will be somewhere here, and this much height is the capillary rise, and this is your uh, capillary tube diameter, and this is your liquid. We are considering water. So what happens here, if you resolve the surface tension forces, they will act on like tangent to the interface, liquid solid interface, and this weight of this column, this liquid column in the capillary rise, which will be the mass into gravity, this g value, and mass here will be density into the volume of the this part. Let me shade it, this part into g. Now volume will be we will consider it as a cylinder, so pi d square into h. So this is the total force acting in the downside, and on the top side we need to resolve the tension force in this direction so that it balances the normal or the weight of this thing. So if it is a tension force in this direction, so we will have cos component of it in the circumferential direction. And so from top view, if you see, it is a circle, right? So the force or the tension force acting on that surface or that periphery will give you the total surface tension force. So that will be where it is, T cos theta. This is the normal force of the surface tension force into pi d. So this will give you force, and here this rho g pi d square into h, the force balance here. So pi goes and 1d will go. Am I missing something? No, right? One second. Where is the Okay, yeah, I think this is the correct way. So here, typically, our interest is how much height did it receive. So it becomes T cos theta and divided by rho g d. So as I said, this capillary rise or capillary fall is a function of primarily function of surface tension theta, which is the angle of contact, and this density, and also the diameter of capillary tube. And what happens in case of capillary fall happens when this theta value is greater than 90 degree. So when theta is greater than 90 degree, cos theta is negative.
So how this is less than 90 degree, this or the above diagram? How it is less than 90 degree theta?
Okay, so one second, negative, and that happens. So if you just look at this surface, it is like this, no?
Yes.
So as I said, and this is the vertical wall. So see, the tangent to the surface is like this. Okay, it can be, you can draw it like this, no? Both ways. So it is like this, okay? And this angle of contact, as I said earlier, is always measured in the liquid. So one way to measure the angle of contact will be from the tangent you start and you go, this way. This will be your theta. Or one another way will be the reverse way. But in reverse way, you are not going through the liquid, right? Liquid is here. So this is your theta. And from the geometry of the figure, this also becomes theta. Understood?
Yes.
So that is how it is theta. And one second, I'll just. And in case of the other case where your, liquid interface is like something like this, it bulges at the top, which happens in case of mercury, and here will be the liquid. So here, if you draw the tangent to the surface, it looks like this. Okay, and now you have to define the angle of contact passing through the liquid. So it will be this angle. So this is greater than 90. So therefore, the cos theta becomes negative, and your h becomes negative.
Yeah.
And therefore, instead of capillary rise, you get capillary fall.
All yes.
Okay.
Got it, sir.
Okay. So I think based on this discussion, maybe you will be able to solve your assignment questions. And my apologies because this discussion was not in a structured manner because there were many concepts and there is no common link between them. But from next lecture, let's say next lecture will be on fluid statics. So there the discussion will become focused on the particular statics part, and maybe we will have more numerical examples also instead of theory. Today it was more theory, but I think it was important. And you can, based on this theory, you can solve your problems also. So that is extension to it, but within this time you cannot do all the things. So I think we are already past 8. So if you have any doubts, you can ask me, or then otherwise we'll close.
So the rho V L D usual rho V T. Yes, Reynolds number, sir. Rho V L.
Yeah. Uh-huh.
So what the L stands for?
In case of flat surface, L is the length of the plate, like maybe like this. And if it is a pipe or something, so there will be D. Instead of L, the diameter of pipe will be there. So it will be rho V D by mu.
Yeah.
Okay.
Yes.
Yeah, thank you. Anybody else? I think some people have already left, so I think we should stop also. Anyway, any other question, or shall we close?
Hello, sir.
Can you?
Yeah, tell me. Anyone? Pradeep
Sir,
or
where
Okay.
is assignment uploaded, sir?
assignment is on the NPTEL website, right? NPTEL Swayam portal NPTEL. Have you registered for the course? You must have, right? Then only you receive the
Yes,
link.
yes, sir.
Yeah,
Yes,
so
sir.
in week 1 introduction, if you click on it, a drop down menu will appear. There it is there, quiz.
Okay. And sir, when you uploaded these notes on NPTEL, sir?
I give them tonight only after the lecture. Then it is in their hands when they give the links to you. But I think it will be done in a couple of days.
Okay, sir.
Okay.
I have a question. Like, can
Okay,
you
tell me.
summarize on the no slip boundary? Like, let's short summary. Like, you can say it in a very short form.
Okay, in a short form, no slip boundary conditions holds for most of the applications in real practice, with some minor exceptions, such as fluid interfaces or very small scale devices in which capillary forces are dominant. And yeah, I think that is the most concise way to look at it. But more or less everywhere the no slip boundary condition is applicable.
Okay, okay, thank you, thank you.
Yeah, okay. I think Aditya and Pradeep are waiting. So Aditya, maybe you can go ahead.
Sir, I was asking that I joined this meeting at 7 p.m. because I had another class at from 6 p.m. to 7 p.m. Is that going to affect my attendance or my performance in the certificate?
Not really, but which, like, you have couple of courses in the same time you're saying.
Yes, from 6 p.m. to 7 p.m. I had another class and I joined this class 7 p.m.
Oh, but this will happen every week, right?
I think every Tuesday.
Oh, see, from my side, there is no problem in your attendance and all, but then you will miss first half of our discussion, right? So
Yes,
anyway,
so I think,
yeah,
yes,
tell
sir.
me. Yeah, I don't think it will affect anything in like attendance at all.
So I can cover up the missed that I have missed the concept. Can I cover it in lecture and those things.
Yeah, you can watch this recorded session later. Maybe you can watch it on YouTube. It will be there, and maybe from there you can cover up the first hour that you miss.
You are going to cover the concept that has been discussed in the lecture only, right? Not outside the lecture.
In some cases, yes, but mostly it will be whatever was taught in the lectures. But what happens sometimes, some additional tips are there, so I will try to add them in my discussions. But yeah, mostly it will be according to the content of the lectures that you see for that week.
So I can do the assignment and give the exam from the lecture part only. So there is no like you will teach something outside the lecture and that will come an exam.
I don't think so.
Okay.
But yeah, if it is inconvenient for you to attend, I think you can see it later also if you want. Otherwise, you can just stick to the class lectures. This will be like a revision class. If you are interested, you can come like that.
Okay, sir. Thank you.
Okay. Yeah, and I think Pradeep was there. Pradeep.
No, sir, I'm done, sir. I'm done already. Thank you, sir.
Okay. Okay. Thank you, everyone. So shall we close now? Okay.
Yes, sir.
Okay. Okay. Chalo. Thank you. Good night.
Thank
And
you,
see
sir.
you.
Thank you so much.
Okay.
Thank you. Very informative, sir.
Okay. Thank you. Thank you. Good night. Bye.
Thanks.
Thank you.
Yeah. Thank you.